So what is ASCE 7 all about? Not everyone talk at once. What's that?
Minimum design loads.
Minimum design loads, right? So if you saw the cover, then you knew what it was about, right? ASCE 7 is where we get our loads from. ASCE 7 determines loads, what loads we use. Now, when we're doing, when we're designing a structure, we're designing a structure. Do we just do what ASCE 7 says? No. There's things called notional loads or construction loads that ASCE 7 has no clue about how something's going to be designed, how something's going to be constructed. But it's your job as the engineer to ask that question or to find out how something's going to be designed. You'll oftentimes find that the loads during construction are much, much higher than the loads they'll see in service. You'll say, well, how do I know how they're going to build it? Okay? Well, number one, you either need to come up with, and if you're in a design-build environment, then you'll know because they're going to tell you how they're going to build it. If you're not in a design-build, if you're in a facility where you just design and then the building's done by another group, then you need to come up with at least one rational way to construct it, right? And usually they'll put that in the plan sets as well. Okay? So where's how you get your minimal loads. That's what we were talking about before. We're going to review a couple things, and then we're going to talk more about connection design today. And again, it's going to be review stuff, but it's fast review. So I'm going to ask first, what is the safety factor we use in steel construction for yielding and fracture? What is it?
0.9 for yield.
0.9. Well, that's the phi factor. That's right. Phi factors equals 0.9, and what's it for fracture? 0.75. And the phi factor, is that the only safety factor we use when we design something? No. What other safety factors do we have? Load factors. Hit your red button next time. Load factors is the answer. That's right. So it's a combination. How do we find safety factor? Well, it's average load factor divided by the phi factor, right? Yeah? Remember that? Yeah? Now, what safety factor do we nominally shoot for yielding and fracture?
1.67 and 2.
1.67 for which one goes with which?
Yield and fracture.
1.67 with the yield, 2 with the fracture. Okay, so why do we have a lower safety factor for yield than we do fracture? I'd argue that fracture is more detrimental. I'd argue that when something fractures, you better jump, right? And when things yield, you can still survive sometimes, okay? You often can survive, okay? Yield is not a hard number that we have to hit, but fracture is something we better respect, right? Okay, so that's why we're able to get away with less fat in our design on yield than it is with fracture, okay? Now, when it comes to LRFD, do we actually have hard safety factors? No. So what's our safety factor dependent on?
The ratio of live load to dead load.
That's right. The ratio to live load to dead load. Why? Why is that? Well, it's because our dead load's we're much more sure of it, right? And our live loads, we're less sure. Remember when we said average load factor, right? Safety factor is equal to average load factor divided by phi, right? Well, if you have more live load, and your safety factor is going to, your load factor is going to be more weighted towards the live load, right? The 1.6, right? You have more dead load, your load factor is going to be weighted more towards the 1.2. You with me? Okay? And so as we showed in our notes last time, safety factors float in LRFD. They're not constant. Okay? And you'll hear people say all the time, oh, I hate LRFD. There's no difference, okay? There's no difference. Okay? It's just how the safety factors are applied. Okay? It's just how the safety factors are applied. And it's the only other difference is that there's this realization that we really are talking about failure. But ASD have been all along, they've just been tricking people. Okay? They've been talking about failure as well, and they've just been applying hard safety factors instead of allowing the float. Okay? Okay. So I say, why are they not the same? I think we answered that. How do the safety factors compare for ASD and LRFD? We kind of answered that. LRFD, the safety factors float, right? Depending on the live load ratio, live load to dead load ratio. For ASD, what are they? 1.67 and 2, right? Yes? Yes. Okay, so I asked this open-ended question. What is structural resiliency? We talked about that last time in class. What is structural resiliency? That's right. It's the ability for other components of the system to help out and help take some of the load, right? This idea that just because one aspect of our system is overloaded doesn't mean we reach failure. Well, we've got to be very careful when we say overloaded. Okay? If we're overloaded something that has the ability to yield and give, then that's okay. If we overload something that's brittle, that's going to fracture, that's not okay, right? It's not okay. Okay? So it's this concept or idea that the system is either going to fail when two limits are reached. Either one, every component has reached its yield, or all the stiffness has been exceeded or used in the system, or when one element gets so overloaded or one aspect gets so overloaded that it just breaks, right? That's this concept. And we're going to see it over and over and over again. So you might as well learn it now, all right? Okay, so, and I had a graphical thing that I showed for structural resiliency, and I had two plates being hooked together with a bolt. You could do a weld if you wanted to too, but it's kind of just fun. It's kind of easier just to talk about bolts. And I had a line that I had drawn on there, and where we were thinking about what the stress was at different points, and I had point 1, point 2, and point 3. 1, 2, 3. And I said for P1, for a low amount of load, what's the stress distribution going to look like around the hole? Is it going to be uniform? Why not? Got a stress concentration at the hole. That's exactly right. And stress concentration, that's going to cause localized stresses to increase, right? Yeah? So right here, locally at the hole, we would expect to see this part to be higher than this part. Yes? Now what's it look like in between? No one really knows, okay? No one really cares either. It is going to look nonlinear. All right? Because as structural engineers, at least at this point in our life and our career and what we're talking about in this class, we're interested in calculating limits. We're interested in calculating when things break or when events occur. We want to avoid them, right? And what happens in between them, that's just complaining. That's just whining, right? That's just extra stuff. We're interested in events, major events, right? Now, oftentimes when you talk to researchers, they're more interested in what led up to the failure. Okay, and I'm not discounting that. And I'm not saying it doesn't have validity or value, all right? But your job is to design things quickly, oftentimes, right? Or get to answers quickly, oftentimes. And you don't want to spend hours upon hours finding non-linear stuff that doesn't matter, right? Yes. Okay, cool. So, we'll draw a stress-strain diagram for the material. We say at this point, P1, load point 1 may be here, load point 2 may be here, and 3 may be down here. 1 point's at yield. Yield! Oh no! Who cares? all that means is that little sliver of steel next to the hole isn't as stiff as the material away from it. You with me? Okay, so how long can we go on this type of connection? How much more load can we take? What's the limit state? Structural resiliency tells us either when one element is overloaded or when all of them, right? So when we talk about elements, in this case, we're talking about this area. When all of this area is at what point? Yield, but actually you'll find out in the code we use fracture. We actually use fracture. We don't use FY, we use FU. FU is, how much higher is FU than FY? 10 to 15%. 10 to 15%. So this idea is that we're going to go all the way through the strain hardening, okay, and we're going to get some. We are going to take that into account, that benefit. And the reason we're able to do that is because the yielding is occurring over such a small amount of area. It's not that big of a deal to the structure. You with me? Okay, we'll talk about cases today when that yielding happens over a much larger area of the structure, and that's not something that can be ignored. All right? Now, every day in class I'm going to be going through a review sheet, and this is over the topics that I feel are important. These are things and concepts that you should also know and should look towards when we talk about exam things, the things that I think are important. Great. Any questions before we go forward? Nothing. Crystal clear. Okay. That's what I want to hear. Okay, in the notes from last time, talked about structural resiliency. I think we've gotten right to the point here. It's just the stuff we just finished talking about today, or in our review. And we're starting to get into connection design. So it's very common in undergraduate classes to focus on tension member design. Well, we're going to review this quickly and then move on to eccentric connections. Okay? Tension members can fail in the following methods: yielding, fracture, bolt shear, bearing and tearing, and block shear. These are all things in tension that you're going to be expected to know and check every single time you have a connection that you are checking and designing. If you have not done all 5 of these checks previously, then you better pay attention and work a little harder, okay? Because the majority of the class has seen all 5 of these checks previously. Great. So let's start with yielding and fracture, okay? And again, we're just going to hit these real fast. When we get to topics that are review topics, we're going to be covering them quickly. When we get to new topics, it's going to take a much longer period of time. So if we have a structure here that's got plates on it, it's got bolts here that's connected with a long piece in the middle, when we talk about the failures, okay, either that being a yielding failure or that being a fracture failure, we're going to be doing checks that are going to be done a little bit differently. And actually, first, if we just talk about the behavior, one reason why we do our checks differently is because the behavior is just fundamentally different, okay? When we talk about something yielding, okay, first of all, the calculation that we ended up using, the yielding calculation, we say something like phi-pn. What's that mean? What's phi-pn mean? Factored capacity, right? The factored capacity, the nominal capacity. Okay? It doesn't mean when it's going to break. That means when it's going to break with a phi factor placed on it. Yes? Great. We use phi, 0.9, times AGFY. What's AG mean? Know your gross. Area gross, that's right. And what's FY mean? The yield, right? And why do we use AG? I mean, AG is the same thing as if I had a plate that looks something like this. That's the same thing as B times T, right? The width times the thickness. Why do I use AG? That's not even the smallest area. The smallest area is at the holes. It's wrong, right? No. It's right. Why do we use AG? Who can help me?
that's where the yielding failure is going to occur?
That's right. That's actually where things fail when they yield. I'm in trouble with this. It's actually where things fail when they yield. And we're going to show a movie of that in just a second. And when things fail, they go and they yield. They go up and they go up and they go up, and then they hit this plateau and they just go and go and go. This is load. This is deflection, right? Right? If you are holding on to the bottom of this and you reached yield, what's that going to feel like for you? Do you know? You're going to be holding, and all of a sudden you're going to feel it go, oh, it's going to give, right? It's going to give, and you're going to fall, and you're going to be like, oh my gosh, right? And you better hope you're not 15% more load than the yield, right? Because if you are, what's going to happen? It's going to give, it's going to give, it's going to give, and then what's going to happen? It's going to break. Yes? Okay. Now, we don't let it get to that point. Okay? We limit it at yield. We limit it at Fy in this circumstance. Why? Well, think about a building. Think about if the wind starts blowing on one side of the building, and that building starts to yield. The brace, the diagonal in that building starts to yield. Okay, so it starts to give. What's everyone in the building going to feel? The whole thing's going to be moving. Right? That's not very good. Right? That's not very good for things like walls in your building, right? They crack and break, right? Things don't fit well together when all of a sudden they start moving 3 to 4 inches to the right. Okay? So we don't let that happen. Okay? We don't let that happen. And you'd say, but Dr. Lay, it didn't fail. And you're right. It didn't break. But a lot of people that own that building would call that failure, wouldn't they? Yes. Yes, they would. So in a sense, it did fail even though it didn't break. Okay? The member yields over the length L. It yields over this entire length. It starts to get longer. It's not a small amount of area that's yielding. It's a large amount of area that's yielding. That's why it moves so much. That's why we don't let it happen. You with me? Great. Member yields over length L, causing large deflections. This occurs over the gross area. Okay? Now, when we talk about a fracture, we talk about the equation for fracture. We say phi(PN). Again, that's the nominal capacity. It's 0.75 A sub E FU. My favorite variable in this class, FU. Right? Now, we're not using yield. Why not? It's past yielding, right? Since we're yielding in a small area, which we're going to talk about in a second, it's okay to yield, right? Yield's no big deal. We're going to allow it to go to fracture, right? When we talk about A sub E, what's that mean? It's the effective area. Another way to think of it in this problem, it's the same as the nominal area. We'll talk about the difference between effective and a nominal. Nominal, that has to do with shear lag. Okay, it's going to be a topic we're talking about in a second. The nominal area is just the gross area minus the holes, right? Now, every time in this class, when we take out the holes, we're going to add 1/8 of an inch. Why do we do that? Because it's slop, right? When you drill the holes, there's going to be some damage done to the side. Some people like to use 1/16 of an inch. A lot of people in practice like to use 1/8 of an inch. Why? Because it's conservative, right? It's conservative. Okay? So oftentimes in this class, we'll see when we're subtracting out the diameter, we'll take out another 1/8 of an inch for the slop. Okay. Okay. There we go. There's the area of the hole is this. There's the area net. So this fracture is happening here, and our load deflection curve looks something like this. It goes up, but it yields, it quickly goes up again, then it fractures. Okay? That's what happens. It breaks. And this break happens at low displacements. It's fracture. It's brittle. That's what that means. Sudden. Right? Okay, great. And then I say here at the bottom, yielding on the net section, A sub E is not important. see the following example for reasons and think about structural resiliency. And then I think at this point, if I can, I'm going to do my best to bring up a movie real quick here. Come on, baby, just play. Oh my gosh. Well, I'll tell you what. I will get the movie figured out for next time. So we'll just keep going. Fracture analysis. Talk about the next page. I say fracture analysis always occurs on a net section. But you must determine the forces on a net section. So here's a little example problem. And this is something that I don't know if you've ever thought about before, but people will sometimes look at a problem like this and they'll say, where is my fracture going to happen? Because in every single problem in this class, when we go to draw a failure mode, we have to draw a free body diagram of that failure. It's required. Okay, you have to draw where is it going to break at. Some people don't really know where it's going to break at, and that just shows that they don't really understand what they're doing. Okay, we're going to make sure you do. So let's just say the bottom member, I mean, this wouldn't have to be done this way, but to simplify things right now, let's just say the bottom member is really big and fat, all right? And we're just looking at what's going on in the top member. And if I'm pulling with a load P here, then I have to be pulling with a load P here. You're with me, right? If not, what happens? It flies through space, right? And we're making airplanes then, right? Something else. Cars at some point, right? Not making buildings, right? Or bridges. Okay. So if I load my connection here, P, and I talk about what load, and in this column I'm going to put what load is in the plate. You with me? And over here I'm going to put what the load is in the plate underneath. Okay? So I'm pulling with P here. I have written here that the load in the plate, the top plate, is P. And the load in the bottom plate is nothing. Okay? And then I have a line drawn here. It happens to be at a bolt. And I say the load in the plate now is only half P. And the load in the plate underneath is half P. What? How can that be? Well, if this load is P, how is the load going to be transferred from this plate to this plate? Through the bolts, right? So if this load is P, what are the bolts going to take? What? Half the load. Well, one could say that they're going to take P over 2 and P over 2, right? Now, if one said that, and they were talking about at failure, they're exactly right. If they're talking about all the points that lead up until failure, it may not be 0.5p and 0.5p. It may be that more load's gone on the one on the front and less load on the back. You with me? So how are we able to say it's P over 2 and P over 2? Or why do we just say it's P over 2 and P over 2 if it's wrong? Structural resiliency. It says that even if I overload the bolt in the front and I go up higher, it's going to cap out, right? And it's going to say, please, I can't take any more, right? And it's going to ask this other bolt for more help. And it's going to, as long as the system is ductile enough to allow that load transfer to happen, it will, right? And it'll keep happening until what? Both bolts are at their limit, right? then structural resiliency will say both bolts will fail simultaneously. You with me? Great. So that's ideally what happens, and that's why we ideally do it that way. Okay? Now it is possible if bolts are misdesigned, okay, or if connections are extremely long and you need lots of deflection to occur to engage all the bolts, then you will get individual bolt failures. And you will not get the full capacity that you think. But that only happens when things like you have slotted holes. Okay? Right? Slotted holes, you have bolts that may be flying around in the holes, right? And in that case, they have things called pretension bolts they make you use, right? So, and at that point, you're not actually relying on the shank of the bolt to transfer the load. You're relying on the friction on the surfaces to transfer the load. All right? So it can be done. Okay? Can be done. It's a little bit different system. So if we have 0.5p here, what do we have to have here? 0.5p, right? Right? And now I'm telling you down here that the load, the stress, is 0. Well, that's not exactly right, because some of that stress has to turn the corner, right? Some of that stress has to turn the corner, so the stress isn't exactly 0. But if I move far away from this point, then it's about 0. You with me? It's idealized, but it's good enough for these calculations. So we can see our load is slowly going out of this plate and into this plate. So if failure is going to occur in the top plate, and it's of the same thickness, where is it going to occur at? I'll ask the question again, because people look confused. If I'm trying to determine, I'm trying to win a bet on whether this top plate is going to fail on line A or line B, which line do I want to bet all my money on? A. Why? It's closest to the load. That's a true statement, but not a very good answer. Why?
B brakes are still, that front bolt is still taking load, so you don't need that half load.
Right. The load in the plate at this line is P. The load in the plate at this line is actually 0.5p, because some of the load is already left. Yeah? Okay. So that's why we know it's always going to fail here. You with me? Now where's it going to fail on the bottom plate? Let's say we're checking the bottom plate. Where's it going to fail at? B or A? B. How'd you know? Because that's where all the load is. By the time you get to this line, you're only resisting 0.5 of P. You with me? Okay. So that was nice and clean and good, but guess what? In this class, we're going to get dirty. Okay? So if I have load P here and load P here, and I've only made it mildly complicated, and I start to lay these things out, and I start to say, where's it going to break at? Is it going to break here in line 1, line 2, and line 3? And don't try to answer it yet, because you don't have enough information. Let's think about it. Okay, let's think about it. All right? Okay, so let's do the same exercise we did over here, but we're going to do it together. And I'm going to draw on this line the load in the main member, or this line. So I'm going to say this, at this point we have P, and this over here is going to be the load that's going to be in the bottom plate. What's the answer? 0. Yay! You got it right. Okay. So now what is the load going to be? Oh, let's do another easy one. Sound good? What's going to be the load here? What? 0. And what's the load going to be here? P. Okay? Cool. That's good. Now let's do the ones in the middle. It's always good to get the easy ones out of the way, right? Yeah. Okay. So what's the load going to be in this plate? 6/8 6/8 P. How'd you get that?
Well, if they're all at their limit state, those 2 bolts would be making 1/8.
Exactly right. There's 8 bolts. We'd all expect all 8 bolts to have P over 8 at them at the limit, right? Every bolt would have P over 8 on them, right? If I've taken 2 bolts out, that means 2 bolts, 2 8s have been given the load to the bottom, yes? And 6 8s. P is still in that top plate. You with me? Okay? Let's go to the next one. What's the answer here? What's that? 3/8 P. How did I know? Well, there's 5 bolts here that were the loads left, right? 5 are gone. So that means this has to be 5/8 P. You with me? Great. Okay, now I'll ask the question again. Which line is it going to break on for this top plate? Line 1, line 2, or line 3? What? Somebody says 1, 50-50 chance, right? Or a third of, 1/3 of the chance. Exactly. You don't know the area of the net, do you? So you don't really know which line it's going to break on, do you? You have no idea. It's probably going to be 1 or 2, right? It's probably going to be 1 or 2. So how would you find that? That's right. You do a bunch of what-if statements, right? You'd say, okay, let's just say I look at fracture path 1. So if I talk about my area net, it's going to be my area gross, right? Minus 2 bolt diameters plus 1/8 of an inch. Why do I do that? Because there's 2 bolts, right? And then why do I add 1/8? Slop. And then why do I multiply by the thickness? Because you got to get an area. You got to check your units. You need inches squared here, and you need inches squared here, right? Okay. So you would find this would be your net area, and you would compare it against the load P. Yes. Then you're not done, are you? No. Then you do line 2. Line 2, you do the same thing. You'd say area gross minus 3 bolts. Why do we use 3? Because there are 3 bolts, right? And you'd see 6/8. So we don't know. We'd have to plug in. We'd have to see, right? We'd have to determine for ourselves. Okay. Now I went ahead and thrown up fracture path 3 on there. But if we notice, the area for fracture path 2 and 3 are the same, aren't they? Yet the loads are different, aren't they? So I know that that will never control. And unless I just like to waste time, which is equal to money in this class, I shouldn't calculate it. You with me? If I see you doing this, I'm going to write on your paper, you must be rich. Okay? And that means you must have too much money and too much time to calculate things like this. You need to use your brain and realize that it's not that important. You with me? Okay? Now if we do the same thing for the bottom, we'll notice it's a little different, isn't it? That on this first line 3, I am subtracting out 3 bolts, right? There are 3 bolts there. But I'm dealing with a load P, aren't I? Yeah? Yes? So I can tell you right now, I know for the bottom plate, it's going to fail where? Line 3, isn't it? Has to. Because it's the same area on line 2, yet the load is lower. And you get this lower area, it doesn't have to. I guess it's maybe in some freak world possible it could fail on line 1. Maybe. Maybe. But I think the probability is pretty low. Okay? Probability is pretty low. Okay? So I can definitely tell you this one isn't going to control. And I'm betting against line 1. You with me? Okay. Now, what can we learn from this? Connectors transfer the load from one member to the other. When connections get complicated, it's difficult to know where it will fail. So how do you decide? Do them all. Or do all probable, all likely connections. Right? And this is why also it's a very good idea to design connections with a uniform thickness, width, and uniform hole spacing, right? Because if they are uniform, you know exactly where to check, don't you? There's 2 checks, right? What if we got something freaky in here, right? With like some connection like this on the top and some connection like that on the bottom, and and they're all different thicknesses, right? The top's a different thickness than the bottom, and now you got all these bolts in here, and you're like, oh my Lord, I don't even know. It's complicated. I'll put another one in the middle, and maybe they put weld on it too, it gets complicated, right? Don't do that, okay? Don't do that. Not on purpose, at least, all right? Okay? Okay, because the simpler and more elegant and easier you can make things to build, oftentimes they're much easier to design. Okay? You know what you're doing. Okay, so now we get the great question, what if the holes are staggered? Because on that previous problem, one of those fracture planes could have looked like this, right? It's possible, right? And we'd like to check that, right? Well, how you do it with staggered holes, that's no big deal. Hopefully everyone's seen this before. You use the S squared over 4G term. So if the failure involves diagonal, the contribution of diagonal is accounted for by using this S squared over 4G times the thickness. This should be done for each diagonal. And why do we do this? Well, it's because simultaneously on that cross section, we have tension and shear occurring, right? So we're not able to get away with just the pure area. Like, if you just took the pure area there, right, that wouldn't work, right? Wouldn't work, because if you just took the pure area and treated it as filling it in pure tension, that's not conservative, right? It's not conservative. And if you took the full area and you just treated it about filling in shear along the length, that's kind of too conservative, okay? So this S squared over 4G is like something in the middle, right? Now, you could easily break out a finite element program and you could figure out that the exact answer, if one wanted to. We don't have time in this world, okay? We've got too many other things to do unless someone's paying you a lot of money to do it, right? That's what researchers get paid for, right? To do some things like that. Instead, we use things like this S squared over 4G, and it just it gives you extra thickness, and I'll show you what it means right here. So this is the way this is going to work. We're going to talk about breaking across A, B, C, D, which you guys already know how to do, and that's not that big of a deal. And then we're going to talk about fracture across A, B, E, C, D. A, B, E, C, D. So we're going to find that it doesn't look that different. We have 3/4. Why do we have 3/4 of an inch? Because it's a 3/4 inch thick plate. Yeah? Okay, that's our thickness. Okay, we have, I say, 10. Let's see. I say, how do I know it's 10? Well, it's a 3/4 inch by 10 inch plate, isn't it? Okay. So 10 inches, that's my width. My entire width is 10 inches. Minus 3. Why do I have 3? Number of holes. This is our diameter term plus the slop. Then I'm going to add to it 2 S squared over 4G terms. Where S is 2, there's 2 here. That's my S. G is here. That's 3 s squared over 4g. That's s. That's g. Let's notice, I acted like it was going through all 3 holes, and then I added in this extra area, or extra length. This is actually length. Extra length to account for the diagonal. You with me? And then multiplying by the thickness. Okay? And it's kind of cool that if you actually do the math on this, the units turn out to be inches. Right? Inches. So they're in inches. There's not an area we're getting here. We're getting a length calculation, this additional length. And it's a prime question for me to ask you, why do we have this additional length? Right? And you could say, because we have tension and shear simultaneously. Right? And we have more length as well, because it's across a diagonal, not just across a straight width. You with me? Okay. So I've got another example problem down here that you can look at on your own, okay, where I'm showing a P and a P. I think I do this calculation a couple different ways, and I find out what the areas are, and I find out where it's going to control. Now, one thing I want to point out, though, on this, okay, this problem is a little strange. We are working the strange, okay? We're working the weird, okay? So this class is really about. I think that means I have 5 minutes. 4 minutes. That means I also need to turn the volume down. Okay, we're going to be working the strange and the weird. Okay? And the strange and the weird this time, we're going to find that how do you work this problem? We're looking at a connection, an angle with staggered holes, right? And 2 holes on the bottom. And we're looking at failure. Well, one failure mode would obviously be straight across, right? Yeah? Straight across, okay? Another failure mode is possibly down, over, down, and then straight across. You with me? Okay? Now, that doesn't seem too hard, okay? We can actually take this plate, imagine flattening this out, right? Rotating this. You with me? And then drawing our failure modes. Here's A, B, C, D, E. Okay, that's calculated down here for you. Here's A, B, D, E. Calculated right there. You with me? Yeah? So we could do that. Now, something's a little weird, though. I'm going across an angle here, and this angle happens to be going through this. Now, when we look at the thicknesses of these plates, we'll find that the thicknesses are not constant. They're constant in this area, they're constant in this area, but they taper at the ends and they taper at the middle. Why?
That's how the steel is made.
That's how they're rolled, right? If this is a rolled section, that's how they're made. If you're using a built-up section made out of plates, it's not how they're made. They're truly going to be then a constant thickness throughout. You with me? Okay. Now, because they're rolled, one would expect there to be more fat in here, right? More area in here. So possibly when we go across this diagonal, we may be able to get extra benefit, right? Because it's extra thick in possibly that section. You with me? Okay, we could try to do that if one wanted to. Okay? But what I'm going to say to you, and this is advice I'm going to give you now that please remember when you're doing your homework, okay? When you can do things that are conservative, that simplify problems, do them. Because if not, you'd have to come up with some way, okay, well, how am I going to take into account this thickness? Well, okay, I'm going to give this extra area a little bit more benefit, right? I'm going to say, I'm going to add about 15 or 20 more % to this area, right? Maybe one could argue that, maybe, possibly. Try to get that past a bunch of engineers. You're engineers. You know how you are. You have friends that are engineers. You can convince a lot of people of a lot of things. Good luck convincing engineers about things that they think they already know a bunch about. They will argue with you all day long. I know I'm one of them. They will argue all day long. Well, should it be 15 or should it be 20? Should it be 10? Should it be 5? Should it be whatever? And then just say, to hell with you. I'll just assume it's 0. I'll just assume it's not important. You with me? And if you can assume something conservative that still works, they can't argue with you. You with me? So what you've just seen is going to be actually another one of the keys to this class, or seeing these things that are conservative, solving these somewhat that look to be hard problems, making a simplified assumption that voila is easy and I know how to do it and it's not that big of a deal. You with me? So guess what? We just made money by doing that. Because you didn't have to argue with people. Right? Right. You save time. There's several other example problems in here. I'm not going to be covering them. Okay? So you can look at them yourself. I'm going to hand out another sheet of notes. Okay? And we'll cover those first thing on Monday.